Yeah, I'm happy to talk to you guys. This is a big crowd. It's nice to see. All right.
Keep quiet because
I'm going-
otherwise it'll be going back and forth. So we're just going to listen to you and then we're going to ask questions when you. So it's not like we're not listening because you can't hear us.
Okay.
We're listening very.
Okay. Well, then I'll do the presentation first. Then. Okay. Can you all see the screen?
Yep.
Great. Okay. So I'm going to give a presentation on Arvo and why we're working on Urbit and what we're hoping to accomplish with Urbit. So talk about the problem that we're facing, the solution that we're working on, and I'll go into some technical details about just the overall stack, the overall software stack that we're building, and what the layers of that stack are and why they're designed roughly the way they are. So why Arvo? And the answer is that the software that we're all running right now on the internet was designed 50 years ago for a very different world. And we're asking it to do things that it was never designed for, such as running an internet with billions of people on it, trying to provide security, and trying to be a platform for personal computing. So these were not in the original design goals of Unix or really even of TCP or IP. And as a result, it's very expensive and difficult to run user-facing services on the internet. And so what ends up happening is that you get a few extremely large companies who are the only ones who can actually afford to run the very large server farms to deal with large numbers of users and actually coordinating information over the internet. And this in turn leads to a lot of social problems. So I say there's no fun anymore here. That's obviously an overstatement, but in general, a lot of the problems that we have in today's world of the internet and computing come fundamentally from technical limitations of the 1970s software stack that we're all still running. The solution to these problems is individual ownership and sovereignty. So basically, each person needs to have more control over their own computer, over their own data, programs, etc. And each person needs to be more autonomous in the digital world. So I don't know if you guys have seen this meme format, but yeah, you will hear a lot of people talk about own your own data, but that's not enough. It's important. You need to have control over your data, but computing is more than just data. Computing is also running programs on that data. So you need to own the programs too, right? If someone else is running programs on your behalf, you don't have control over what programs they're running, what they're doing with your data, et cetera, with your data. And so really what you need is your own server, right? So you need to be running your own programs, and also you need to be running them in a way where you can communicate with other people. Other people can find you, right? Other machines can find your machine. And so you need to have a server that can listen for incoming requests from other people. So you need a server. If someone else is running the server, same problem. So it has to be something you're running yourself. And in order for other people to find your server, it has to have an identity. So in Urbit, we have an address. It's a number. Typical address is 32 bits. And it's also pronounceable. So I'm Ravnus Rikfer. That's a 32-bit address. And we call this system Urbit ID. It's documented on the website. But the idea is that this has an identity. It's a permanent identity. I can sell that, but I don't want to. Most people will not want to sell these things. It's something where you want people to know you as this, and You want to have a reputation associated with that, and you want to have a stable identity. Just like in real life, you generally want to use your own name and not change your name every year or two. And so this is sort of a name like that, but for the digital world. And that identity is associated with a cryptographic key pair so that communication with other servers can be secure. So then you need a couple of other things. These are a little bit less obvious, but you really want this, because this identity is permanent, and because just in general, we want to store things that we care about for our whole lives. If we have photos of our families, we want to keep that forever. And we really want to give it to our children and grandchildren, right? Like, just like if you have, letters and photos that are physical, right? That are written on paper, you also want to hold on to those. You want to at least have the ability, if you want, to hold on to those forever, pass them down to your descendants. And it's very difficult to do that when in the current digital world where everything is scattered among dozens, tens of different services. You got Dropbox and Facebook and Twitter and all this other stuff. It's not all in one place, and those can come in and out of existence. They can stop and start, and it's easy to lose sort of pieces of the data that you care about. So part of what you need from this server is you need to be able to move the server from one machine, physical machine, to another physical machine, because our machines don't last our whole lives. They update, new technologies come out, hard drives die. We have to be able to, so this, whatever we have here to manage our digital life, whatever server we have, it has to be portable. We have to be able to move it from one machine to another. So the standard solution for this is to use a virtual machine. So we have a virtual machine in Urbit. And here are some requirements of this virtual machine. It can't lose your data, right? So it has to have some sort of persistence mechanism, has to write these things to disk. The way it writes these things to disk has to be done well, so it can't lose anything. It can't use any code that's specific to one operating system, right? Because if you're running a Windows laptop and then you later switch to a Linux laptop, this virtual machine, your server, your personal server, can't just stop running, right? So the way that this thing works needs to be specified in a way that doesn't depend on which operating system it's running on. Finally, it needs to, there are two more. It needs to be auditable, which is really part of the idea of how you need to be able to manage this yourself. You need to be able to inspect it, make sure it's okay, etc. And it needs to update itself over time. This is both to fix bugs and also to, mostly for security. Cryptographic algorithms change over time, the algorithms don't change, hopefully, but which algorithm you use changes. And it's important to be able to keep up with the times in that way. And so the operating system really, this virtual machine, really it should handle that itself. You shouldn't have to do that as a user. It should keep itself up to date in such a way that it stays secure. And this is actually one of the things that's really hard about running your own server these days. How many of you have run a server on the internet? Raise your hands if you've run a server.
Raise your hands if you run a server. Can you? I don't know if you can see. Well, you can see a few, like a 5, 6 hands, definitely.
Okay, yeah. It's not really something that you want to do for fun, right? I mean, you can, but if you're serious about it and you want to make sure that it doesn't get taken over, it's a lot of work to try to keep that thing up to date and try to make sure that people don't come in and hack it. It's definitely not something that you want your grandmother running just for sharing her photos with you and making payments. Right, so when we talk about having a virtual machine like this, often people say, well, why not just do something else, right? Why not just run your own HTTP server on Linux? But unfortunately, this is a joke. The vast majority of people are never going to do this. It's way too much work. Even for trained system administrators, it's too much work and too risky to try to do yourself. So this is unfortunately laughable, and that's why we're working on Urbit. Another group of people will say, why not have all your data and all your programs live in a vast sea of interconnected machines where your data is distributed among all of these, and there are economic incentives to try to get people to hold on to your data, sort of like BitTorrent or something, and then you can have all your programs run on some blockchain, and then you can use zero-knowledge proofs to make sure that other people can't see what kind of program you're running. And if that existed, if that worked, it could be cool, but it's not feasible at the moment. That's not something that is really, that can be built in a way that everybody can use. So that's more of a dream, really. Urbit is a dream too, but it's a dream that we run on a day-to-day basis. So this would be nice to have, but it's not very practical at the moment. And if it is, I know some people who are working on parts of that, and if that does come into existence, then Urbit, since it's specified abstractly, actually could move to be run in a way that's like that. But that's not how we're thinking of it at the moment. And then there's another group of people that say, why don't you use Haskell, or why don't you use some existing language and write Urbit in that? Why do it all from scratch the way that we're doing it? And the answer to this is more complicated. But the short answer is that there are no existing languages or pieces of software that were written to solve this problem, right? That were written to have this virtual machine that you can update, that can update itself over time, that has an identity, that is portable. And if you look into trying to write this in Haskell, you will very quickly run into problems with trying to reload code, which you can use GHC to do that, sort of. And any particular, you can look at Lisp, you can look at Smalltalk, or you could look at WebAssembly, and look at a WebAssembly VM. These are all options. I think the most viable alternative to Urbit would be a WebAssembly VM. And there's something called the WebAssembly System Interface, WASI, which I think is actually the biggest competitor to Urbit. It's not obvious that it would be, but that's the way I think about it. So the trade-off there is that Urbit makes a trade-off in favor of simplicity. And we lose some performance. So Urbit is not as fast as a lot of other things. But what we gain is something that's simple enough that one person really should be able to understand the entire software stack, which is a very unusual claim to be able to make. So maybe after the talk, if you guys are interested, we can talk about this some more, about how Urbit sort of makes these trade-offs.
Sorry, it just takes me every couple of seconds to turn on and off back the mic. Yeah, just go on. Whatever, the more the merrier.
Okay. So all right, so now we have this virtual machine, right? We've decided that what we need here is a virtual machine. Has to be portable. It has to have an identity. Has to be able to be run as a server. And so here are some of the design principles that we use to guide the decisions that we make about how to build Arvo. So one is that it's abstract. So Urbit is abstractly defined. It does not, the only things required, the only concepts required to implement Urbit correctly are our data structure, the noun, which I'll get into in a bit. The idea of and implementing the knock specification on those nouns. And then there are a couple more layers that are, there's a way of serializing those nouns and deserializing them. And there's a protocol between the runtime system, which we call var, and Arvo, which is the virtual, the stuff that we're running inside of Urbit. I might call that the OS. I mean it as sort of an overlay OS that we run on top of Linux or Mac OS. I'll get into that a bit more. But basically, Arvo needs to be abstract. It shouldn't be defined in terms of some particular machine, some particular operating system. It should be defined in terms of pure mathematics so that it can be guaranteed to be transportable from one place to another place, from one machine to another. Similarly, it also needs to be isolated. So the kinds of interaction that it has with the host OS need to be very well defined, very simple, and also need to be defined abstractly. So the protocol for communicating between Arvo and the host OS needs to be specified, frozen, and you know, like Urbit should not be making Linux syscalls directly, basically is what this means. So deterministic and persistent are the next two. Determinism is useful in itself, and so it's good for a software system to be deterministic in general. And what we mean by deterministic here is that if you give the system an input, it will give you the same output. Right? If you give the same input once, right, and then if you were to start from that same state a different time and give the input, it's going to do the same thing each time. You can predict what it's going to do. So the other way of expressing this is that the state of this machine is a function of its input history, the sequence of inputs that it receives. There's a function from that sequence of inputs to the state that it will be in. And because, if that's actually a mathematical function, then that gives you determinism. And that's how we do it in Urbit. And persistent, this thing needs to store your data and not lose it. So what we do is we actually just write every incoming event to disk. And we occasionally also take snapshots of the current state as an optimization. But our persistence is guaranteed by writing each incoming event to disk before we act on it. And so that's part of how this machine needs to work. Our persistence implements what's called a single level store, which means that from inside of Urbit, there's no difference between just RAM and disk. Basically, we sort of assume that everything is in RAM. And in fact, the host operating system might page parts of the data in and out of RAM between the RAM and disk. But from the perspective of the internal software, it's all in RAM. And if you lose what's in RAM, you can always reconstruct it by rerunning the events. So this is part of how we get to deterministic and persistent. And this is part of what makes this thing portable from one machine to another. I'll also go into a little bit more detail about that. And a lot of these, a lot of the properties that I've talked about here are designed to help you get to be a manageable system, right? So you yourself need to be able to be your own system administrator for this, and that should not be a full-time job. It should be pretty easy to do. And even someone who isn't a software engineer or a professional system administrator needs to be able to manage this thing themselves. So that's a tough goal, I think. That's really the hard part here. And this is why we pick simplicity over performance in general, is to try to get us closer to this. So the system as a whole consists of a stack of layers, and so starting from the bottom, we have a universal data format called a noun. So it's a recursive data structure. It's a binary tree of numbers. And what we do is we take all of computing and we represent it as a noun, right? So the state of your operating system is a noun. That includes programs, files, the current state of programs, and all data structures that you might want to use. They're all expressed embedded in this data structure. And this data structure has a very simple serialization and deserialization format, so that we can take the whole state of your operating system, serialize it, move it to another machine, and run it from there, and deserialize it back into the same tree. So everything's a noun in Urbit. And this simplifies a lot of things. So on top of that, we have the event log. So each event that comes in that gets written to disk, that's expressed as a noun, and it uses the noun serialization format to write that event to disk. So this is and there's a specification for the format of this event log, so that you can take the log of all the events and move it to a new machine. And one way of thinking about this is that it's like a database, and one way of thinking about Urbit in general is that we took something like an operating system and stuffed it into a database. So every event that comes in gets written to disk, and you can serialize everything. You can move it from place to place, and you can do event log compaction and truncation, just like in any other database. That most databases are also what are called prevalence systems that use an event log and checkpoint, and so Urbit is not unusual in that way. It's just unusual to implement a personal server or as a prevalence system. So, okay, so we've talked about we have this data format, the noun, and we need to represent not just data in that, but we also need to represent programs in this format. And so we have a language called knock, which is a way of embedding the abstract syntax tree of a program in this binary tree. And so there's just a format for expressing a mathematical function, partial function. Inside of this tree, it's a language with about 12 opcodes. The specification fits on a t-shirt. And so this is how you represent a program inside of Urbit. And in fact, your whole operating system is just one program that runs other subtrees as other programs. So this is our machine code language. So the thing that runs Urbit, the runtime system there, is a knock interpreter. It interprets this knock, and that's basically all it does. So knock is a machine code language. It's not very easy to write or read as a human being. So we also have a programming language, Hoon, that compiles down to knock. Hoon is a statically typed pure functional language. And it's designed to be a thin layer over knock. And in fact, it is. And if you want, I can give you some examples of that. But when you look at a Hoon expression, once you know what you're looking at, you can tell what knock that will get compiled down to just by looking at it. It's a very simple transformation from Hoon to knock. And so then we need to actually implement the program that is your operating system, right? The kernel, like what does this thing do? So we call that Arvo. It's a little confusing. We talk about Arvo meaning the whole state of your virtual machine, but we also use it to refer to just the kernel of that virtual machine. And so we call it an operating system kernel. It does not have a hardware abstraction layer, so it's not exactly an operating system. There isn't really a word for what it is. So sometimes we call it an overlay OS, the way that, say, TCP/IP is an overlay network, because Arvo is sort of like an operating system that you run on top of your normal operating system, and Arvo treats Linux as though it's a BIOS, basically, right? So Arvo, relies on something to be a hardware abstraction layer, and it relies on something to actually, have a knock interpreter. But then, it's an operating system in the sense that it manages different programs, lets you install new programs, update programs, manages inter-process communication, which are just function calls, but it, from the perspective of writing an application, it very much feels like IPC. And then finally, the last layer, there are other layers here actually above Arvo, but one that's really worth mentioning is AIMS, which is Urbit's networking. So this is how we get all the way from just an abstract spec up to a personal server, right? So what makes it a server is that it's on the network and it's listening for requests, and it can send messages to other servers. So any two Urbit ships, a ship is our word for an Urbit instance. So you run your own ship. Any two Urbit ships can send messages to each other using this peer-to-peer protocol. It layers over IP and UDP at the moment, but it's an overlay protocol. So we could actually run it over something else, such as if we wanted to run it anonymized, for example, you could imagine running it over I2P. And it's a packet-oriented connectionless protocol. Every packet between ships that are in the public key infrastructure is encrypted. So in general, every packet is encrypted and authenticated, so you know who it's coming from. And that's end-to-end encrypted. And there's also there's a federated hierarchy of routing nodes. The 8 and 16-bit addresses are routing nodes. We call those galaxies and stars. I'm not going to get into that too much, but if you're interested, there's documentation on Urbit ID, which explains the routing hierarchy. But in this talk, I mostly want to get into the technical meat of Arvo and what it does. Okay, so how many of you have read about nouns, Urbit nouns? Yeah.
Okay, so including myself, 3 people.
Okay, great. Okay, well, I'm glad I have the slide then. Okay, so a noun is either an atom or a cell. An atom is a number and a cell is a pair. So you either have a number or you have a pair of nouns. And the numbers can be as big as you want. So they're like a big num. So they're not a fixed width 32-bit integer. That's not the idea. It's just a number that can be as large as you want, 0 or bigger. So 42 here, that's a number, that's an atom. This long hexadecimal string, that's an atom. You can have a string of characters. That's also an atom. You could have an image file as an atom. Right? So anything that you can express as a byte string, you can think of that byte string as a little endian representation of a number. And we do just standardize this. We just say Urbit is little endian. But anyway, so the leaves of this tree, where we have a binary tree, every leaf in a tree is an atom. So we can also have pairs of nouns. So here's a pair of atoms, 37 and 38. And we write this with square brackets. So bracket 37, 38. And then we want to, so I'll give an example or two of how we embed other data structures into nouns. So here's a list. And this is a list of characters. So it's a string. So this is the string Urbit. So you see at the bottom here, it's URBIT and then tilde, which is null. So it's just the atom 0, but it's a null. This is a null terminated list. And you know, and what it looks like in C, actually, the memory representation of this looks just like the linked list. You can see here, I mean, the linked tree, I guess, binary tree. But it's a very simple data structure to implement. So, you know, so here we have, you know, Urbit, you can see it on the left here, right? And this is a recursive data structure, this list. So, you know, sig null is a valid list. It's just the empty list. And also, here's an example of a knock program. Right, so this is a function, and this is actually the decrement function. So this is code for, you know, subtracting 1 from a number, which it does recursively by adding 1 to 0. And we don't actually run this code. The interpreter matches this particular expression and just runs, you know, uses the processor's ALU to run decrement directly. But this is the specification for it in knock. So you can see, you know, it's not too bad. 8 means declare variable, 1 0 means constant 0. Next 8 here is declare another variable. This is really where we're declaring the function itself. 1 means produce a constant. So this is a constant function, right? Like it's just a literal function here. 6 is if, 5 is equal. 406 here is you know, add 1 to the argument. 07 means look up from the environment, etc. Right. So it's you know, you don't really want to write code this way, but when you see it, you can more or less tell what it's doing. And it's a pretty concise. It's a short, compressed way of expressing a program. So everything is this. Everything in Urbit is just these nouns, just these trees of numbers. And so at any given time, the state of your operating system, or the state of your Arvo rather, is the state of your Arvo is just one of these trees. And this is also the way we represent incoming events from the operating system, from the host operating system, and output effects from Arvo to the operating system. So I'll talk a bit about how Arvo works, like what the sequence is, about what it does. Like, and it's an event-driven system. So it can receive an event from the host operating system. So let's say it receives a key press event. You know, I press the enter key. The runtime system var, the VM, converts that to a noun, sends that into Arvo. So it runs the knock function on this new event. And then that produces, well, after we run it in Arvo, then we take the event and we write it to disk and append it to the event log. And then once that's been written to disk, then we take the effects that were the result of running Arvo, the result of running knock on this event. We take those effects and we actually perform them. So let's say that Arvo emitted an effect that said, you know, draw a line of characters, you know, write a line of characters to the terminal. Then the runtime will then perform that effect once the event has been written to disk. So it's a transactional system, right? If Arvo crashes in the middle of trying to process this event, then the event never happened. It doesn't get written to disk. It's not part of the event log, right? So event either happens, runs successfully, or never happened at all. A lot like a database. Yeah, so here's an example for an HTTP request. This is one of the things that Urbit can do, is it can respond to HTTP requests. It's also an HTTP client. But here it's acting as an HTTP server. So, so it gets an HTTP request coming in from the host operating system, you know, Mac OS, Linux. var turns it into a noun. So var, again, is the VM, the runtime. So that's the program that you run on Linux that implements Urbit. So var turns this into a noun, and it looks like this, right? It's a cell, it's a pair, where the beginning of the pair is a tag saying what kind of event it is, and then there's a bunch of content in the tail, depending on whether it has some tree shape, depending on what the tag was. So yeah, for an HTTP request, it's got the headers, and it's got the actual body of the HTTP request. So var. Okay, sounds good. Can you guys hear me okay? Everything good? Okay, good. Just checking. Okay, so the next step is that var runs Arvo, right? It runs knock on the incoming event, and among other things, that produces an HTTP response. So then once it's run that, it knows that Arvo ran successfully and didn't crash. Then var takes this noun, serializes it, writes it to disk, and once it's heard back from the disk that we confirmed disk write, then we can take the effects, read them, and let's say that there's an HTTP response effect, then it will actually go ahead and send that out, like actually perform the effect, send it out over the wire. Right, so this is another example for a key press. The host operating system generates a key press event, some kind of interrupt. Var receives that, turns it into a noun. In this case, the tag on the noun is a string saying key press, and let's say it was the key was enter, and this will probably just be whatever the ASCII code is for enter. I guess it's 10 or 13 or something, and then the new line. So then again, var runs Arvo on this. Let's say that in this case, this triggers Arvo to send a UDP packet, an AIMS packet. So then, again, same thing, take the incoming event, write it to disk, serialize it, write it to disk, and then once we've heard back from the disk, go ahead and read the effects. So the effect, in this case, there's just one effect, which says fire off a UDP packet. So it goes ahead and sends the UDP packet over the wire. How does Arvo process the event? All it does is run the knock function. And it runs it as a transition function. So this is how we transition from one state to the next state. So the state of Arvo gets threaded through this function. So it's the output. So the state of Arvo is this old Arvo here. All right, that goes as an input to the knock function, along with the new event. All right, so this transition function goes from new event and old Arvo, and it runs knock to produce effects and new Arvo. So the next time an event comes in, this new Arvo here becomes one of those two inputs to the next time the function runs. And so these are all just nouns here, right? So from the perspective of inside of Urbit, it's only ever this function. That's all it ever implements is this transition function. And in fact, so this is the signature, the type signature of Arvo itself, like the operating system. This is the type signature for the operating system, and this is also the type signature for each of the kernel modules, and it's the type signature for an application. So this pattern is used in many different parts of Urbit, and it's a very sort of general way of using pure functional programming to express a stateful event processor, right? Where when it can receive an event, update its state, emit some effects, transactionally, right? So so we will use this internally in programs, and we even have some special syntax in Hoon for making this easy to write. So what do these effects look like? They're a list, right? A null terminated list, just like URBIT earlier, right? So here we have effect 0, effect 1, effect 2, and null. Some events don't emit any effects. That's fine. But this is all that Arvo ever does, right? So here's an example with the HTTP request, right? We get an HTTP request coming in that produces just one effect, which is a pair of string HTTP response, and the ... there is would contain the headers and the body of the HTTP response. Yeah. Okay, so that's at a high level what Arvo does. But internally, what does the kernel do? The Arvo kernel. And what it does is it really doesn't do much. All that Arvo does is it dispatches the event to one of its kernel modules, and then the kernel module ends up handling it. And so there are, I think, 8 total kernel modules at the moment. 5 of them deal with input and output. So if the event that comes in is tagged with an A, that %A there is that means just a string with just the letter A in it. And so if it's tagged with A, then Arvo routes this to aims. And I say route to aims, but it really just calls aims. Aims is another transition function. So Arvo calls that, and it calls it with the new event. So aims is for peer-to-peer networking. Behn is for timers. But if you want to learn about Urbit, I recommend reading Behn, B-E-H-N. It's in package Arvo sys Behn in the repository. But Behn is very short and very simple, so it's a good one to read. It's also one of the more modern kernel modules. Some of them were written years ago, and so the code style is harder to read. We're still learning about good programming patterns in Hoon, and we keep getting better at it. So Behn is newer and a little easier to read because of it. But so Behn is for setting a timer. That basically an application can ask Behn, or another kernel module can ask Behn, hey, please set a timer at this date. Behn will then emit an effect out to the runtime. The runtime will hold on to that timer, and when the timer expires, the runtime will inject a new event saying, hey, your timer expired. Arvo routes that to Behn. Behn then says okay, that timer is done, and it sends an event back. It asks Arvo to route a new event to whatever Behn asked for it. I'll get into the how Arvo dispatches between Behns, between kernel modules, in a little bit more later. But anyway, so we have aims for sending and receiving messages to and from other ships. Behn for setting timers. Clay is something like a file system. It's a little bit misleading because, again, everything inside of Arvo is just in memory. But Clay is a revision control system like Git, but with paths. So you use it like a file system. It's referentially transparent, which is nice. So that means that a path actually includes some sort of version number in it, and then you can never change the value of the file at that path. All that you can do is add a new file at a new path with a new version number. So that's a very nice foundation to build on. And you can synchronize the Clay file system with a folder in Unix, like a folder in your host OS. So that lets you copy files into Urbit. It lets you copy files from Urbit back out into into your Mac OS or Linux machine. So that's useful for development, for copying in files that way. So that's the communication here, right? That's why the file system is doing input and output, is for synchronizing files between inside of Urbit and outside. Dill is our terminal driver. So Urbit has a shell. Dojo is the name of our shell, and our chat program also uses the terminal driver. So there's a command line interface to Urbit, and this is the way that Arvo manages that command line interface. The final input output channel is HTTP. So that's air. That's actually since been this slide is a little out of date. Now air, EYRE here, is the HTTP server, and there's a separate kernel module that's an HTTP client. That one's called Iris. So that one's been split, but it's just but these are the 5 I/O channels. So as I mentioned, each vein, a vein is our name for a kernel module. Each one has its own transition function, right? So for aims, let's say you have it's just a function from an aims event and the old state of aims to some effects and new aims. So let's say that it receives a packet, a UDP packet. It might emit a list of packets to send out, and a new version of itself. So for example, let's say that we've sent a number of packets that are part of a message already, and then we get an ACK, an acknowledgement on one of them. That might trigger us to delete the ACKed packet from our state. All right, so new aims here on the right will not include the packet that just got ACKed, and it might also trigger us to emit a bunch more packets, the next few packets in the message. The aims has a congestion control system very similar to TCP, and so this is actually a totally realistic example of what might happen with aims. Right. So the next one is that what happens to these aims effects, right? These packets. It's Arvo running the vein, right? And then the vein emits these packets, so then Arvo has to deal with these packets. And what Arvo does is it looks at the it looks at the effect, right? Each one of these packets here is an effect from aims. So for each one, Arvo looks at it, and it can tell whether that effect is meant to go straight out to the outside world, in which case Arvo goes ahead and enqueues it to be released at the end of this event. Or it might be an effect that's supposed to be sent to another vein, right? So so here, I'll go through a couple of examples, which I think might help explain this. Let me know how I'm doing on time, by the way. I feel like it's I know it's been a little while. Or do we have a time limit here? Okay.
Can you hear me, yeah?
Yeah, okay, I can hear you. Okay, so I'll wrap up in the next 5 to 10 minutes. So I'll go through a couple of examples of vein activation, because I think this is very helpful for understanding overall how the system is layered. All right, so we get a key press. So we've got var Unix on the left, and to the right of this vertical line, we have Arvo, which is inside of Urbit. So this whole sequence starts when a key press event comes in from Unix. So that gets sent to the Arvo. The Arvo kernel sends that up to Dill, which is our terminal kernel module. let's say that dill then emits a terminal effect, right? Says, hey, write a line to the screen, draw a line, write a line of characters out. So then the Arvo kernel receives that effect and says, okay, I know I'm supposed to send this all the way out to the runtime. So it goes ahead and does that. And so then once this is done, var then performs this terminal effect, actually writes it to the screen, right? So that's the end there on the left. All right, so 1, 2, 3, 4. This is the sequence of operations. But let's say that there's a slightly more complicated thing that happens. Let's say that what dill actually does is it says, oh, I'm supposed to route this key press to the Dojo shell app. That app is run by Gall. So Gall is one of the other kernel modules which runs applications. Right, so you can just install new programs in Urbit as you go, and those programs will be run by Gall. So the Dojo shell application might be configured to, and it is, to listen for incoming key press events. And so now this time, the first thing, key press gets sent to Arvo. That's 1. Arvo sends to dill. That's 2. So far, that's the same as we've had. But then now dill is going to send a different event. It's actually going to send a different effect. Instead, this emits an effect to Gall saying, hey, Dojo, you were asking for key press events. Here's a key press event. So that's number 3. So dill emits that effect back out to the Arvo kernel. But then this time the Arvo kernel says, okay, this is an effect for another vein. I'm not going to emit that out to the runtime. I'm going to send it to Gall. So then it calls Gall with this new event. So that's number 4. And then in this case, Gall actually
Не, ну да, под шашлычок и под пол-литра.
Send it back to
Нет,
Dill
сейчас мы
saying,
еще 5 минут
are you still there?
сделаем с... Okay, Ted, can you hear us again?
Did I lose you?
Right. Там, по-моему, выключен микрофон. Just 1 second. Yeah, can you hear us again?
I can
Okay, thanks.
hear you again now.
Yeah, thanks.
Our internet is over.
Okay. So basically, Dill says, hey, Gall, you asked for a key press. Here's your key press. Gall says, oh, okay, I'm going to run Dojo on that key press. It runs Dojo. Dojo says, emit a line back out to the terminal. So it's going to ask Dill to do that. So then Gall emits that effect. That's number 5. The Arvo kernel says, oh, I know I'm supposed to route that to Dill. So it routes the second event to Dill. That's number 6. Dill says, oh, somebody asked me to emit a line to the terminal. I'll go ahead and do that. So that's number 7. Emits it back out to Arvo. Arvo says, this one's supposed to go out all the way to the runtime. Number 8, terminal effect. That's it. So there you go. That's a full example of Arvo routing between kernel modules. And this is how everything works in Urbit. That's basically all it does. The only other thing that Arvo can do is reload itself with new code, which it can do in a single event. So very briefly, unfortunately, don't have time to get into this, but these are some tough things that Arvo does that are difficult to solve in other ways, or difficult to solve in general. So when we run user space programs, that uses a metacircular evaluator. The function is called mock, not knock, but with an M instead of an N. So you can find that in the language definition inside of Arvo. And so this is how we run user space programs. So we actually have a metacircular knock interpreter written in Hoon. It's pretty cool, and it runs at full speed because of Urbit's jetting system. The thing where the runtime can match a piece of code and just run a faster version of it. We can compile code at runtime, right? So this is how we install programs from source. The kernel can update itself and run data migrations. Also, all the kernel modules can run data migrations, and we have support for letting each application run data migrations. And in fact, we push out new code to the Urbit network all the time. over the Urbit network itself, and all the ships just upgrade themselves all the way from kernel to kernel module to application. We do this all the time. And finally, this makes a very small attack surface in security, right? So this is part of how we make this thing manageable. Going back to the social aspects of this, you want to be able to manage it yourself, and part of that is that there's a very small attack surface here. There's only one deserialization function. This thing is totally isolated. It's memory safe. There really aren't that many things to attack. And finally, there's a peer-to-peer network with this the routing system that I didn't get to describe, but that's also fairly complex. And AIMS as a network has these properties, right? It's peer-to-peer. You can do the peer discovery. That's all handled for you. So when you're just running your own server, you don't have to worry about it. It has a good public key infrastructure that's decentralized. It's authenticated, encrypted, and it has better guarantees than TCP. So it's both transactional and it has exactly once delivery. So these are something you can implement with TCP, but people usually don't. So in conclusion, you need a server. This is how we get there. Might seem a little roundabout, but I think you can see why we did it this way. And so building all these things in this way helps us get to digital sovereignty, so that each person can run their own machine or run their own server. We can communicate just peer-to-peer and have a little bit of a saner world. So thanks for listening.
Thank you. That was fairly easy to intake, I think. Right, one question I have from the crowd here is, what's your current roadmap for developers SDKs? Maybe for different examples for developers that they can look at and see what tools they can develop and so on and so forth.
Sure, yeah. We do have some examples on urbit.org. So we have some example applications that you can start from. So these are Urbit that are written in Hoon. And our roadmap for this, we're actually planning on hopefully pretty soon having more documentation on how to write Urbit interfaces. Let's see. I'll do my stop screen sharing here. There we go. So we're hoping to have more documentation soon on how to write web client how to write web clients that communicate with Urbit. Right, Urbit is an HTTP server, among other things, and so the way that we serve our graphical user interface is over HTTP at the moment, at least. We might change that, but we're going to have more documentation for how to write web clients of Urbit, so that you can build more user-facing applications. We're also working on making the system easier to. So I don't have a real hard timeline for that, but it's something we're working on at the moment, I think. And the other thing that we're doing, though, is we're cleaning up the way that an application is run and the way that an application talks to the kernel and asks it to do stuff. So there is a system called Spider that was written recently. That's in /app. You can find Spider, and what that lets you do is it lets you run these sort of asynchronous computations that we call strands, and they're actually very nice. They make some of the harder parts of writing apps in Urbit make them a lot easier, because it lets you sequence a bunch of I/O operations monadically, similar to how you would do like with the Haskell I/O monad, so you can find a bunch of examples of those in the /TED directory. No relation to my name. I didn't name it. But anyway, the /TED directory inside of the Urbit repository, it's package Arvo TED, that has a bunch of files that use this new paradigm for writing application code. So, and we conduct Hoon School, so you can sign up and it's free, and we have a couple of guys that will teach you how to write Hoon, and so we have a couple of different courses there that we offer.
Еще вопросы? I'm just gonna check if people have questions. Yeah, we have a question. I'll translate. Don't worry. The question is whether the encryption happens. Say it again. I was gonna. Good. I'm trying to translate it. Somebody wants to translate this for me. Basically, the question is whether the encryption happens in a classical way from.
Yeah. Okay. So this is a good question. So we use the ED 25519 elliptic curve crypto, and we use an implementation. It's one of the standard implementations. I can't remember if it's. I mean, it's probably written by Bernstein. I can't remember what the name of it is, but so that's written in C, right? There's a standard implementation written in C, and it's written in C to make sure it's constant time to avoid timing attacks, right? So that's the implementation that we use. But we use Urbit's system called jets, so that the specification for it, in terms of the specification for that function, is actually written in Hoon. But then the runtime matches it. It knows about this particular function. And so then it says, oh, I know that I can run this function in this particular way using the C implementation. And so it runs the C instead to make sure that we don't have timing attacks. It's faster too. So the answer is, yeah, we use standard crypto, we use existing implementations, but we specify them in Nock so that logically Urbit is still completely abstract, right? It's like we do have an implementation written in C, but it's just like our implementation of decrement or other mathematical functions, where they're sort of like compiler built-ins, but they're extensible. So Urbit's jet system is also documented. So if you're interested in this question, I recommend reading about the jets, because it's also a part of how we make certain pieces of Nock performant. All right, Nock only has 12 opcodes, so it can't have all of the different optimized arithmetic operations that a modern processor will have. But we can still take advantage of those by having the runtime match expressions that are written in Nock and say, okay, this is add, this is subtract. Like I can use the arithmetic logic unit on the chip to run that instead of running the functional specification.
Yeah, and the last question was, can the file, the Clay file system, can be compared in any way to IPFS?
Not really. It's very different from IPFS. So first, the big difference is that all of Clay, all of your own files are just sitting on your machine, like on your hard drive. You can run your Urbit either like on your laptop or in your closet, or you can run it on on Amazon Web Services or Google Cloud Platform, right? Like you can run it in any of those places, but it's you're running it. You're running it on one machine, and so all of your Clay files just live inside of your Urbit tree, right? So they're not shared the way that IPFS files are shared. Now, internally, Clay does use hash addressing, so it's content address. So that's similar to IPFS in that way, but that's really just done as an optimization inside of Clay. Now, it would be nice to have Urbit communicate with IPFS. A lot of Urbit people, like a lot of people who are interested in Urbit are also interested in IPFS. So I think it would be cool to see someone write an interface between Urbit and IPFS so that Urbit could say, hey, IPFS, please store this file at this hash. So that could be interesting as an integration, but they're very different actually.
Let me just say that we actually have a bounty for it. I'll tell you later. So if you want to write one, we'll pay you for that.
Oh, cool. That's great.
Yeah. Shall we wrap up? Say thank you to Ted one more time. Maybe a round of applause. Thank you. Yeah.